You know, there's actually, if you want a preview on that, there's a sheet in our documents folder because I handed it out to A Block today that says linear test review suggestions. It's got that information. I'm going to pass it out in here Thursday. No, their test is Friday also, but I don't see them Thursday. They're one day, kind of like one day ahead of you guys, but they catch up by Friday. No, it's a typical day, whatever it is, just shortened blocks. Except for this. This is the longest block. 40, a little over 40 minutes. Everything else is 35. Now that we have all that recorded over the problem. All right. So, number 8. We're doing number 8. All right. In number 8, baseball is seen to pass by a window 20 meters above the earth, above the street at the vertical speed of this. The baseball is thrown from the street. Ooh, what do we know about the baseball right away? It's in free fall. Excellent. So this is number 8. It's in free fall. Folks, I'm having a hard time hearing myself, and I'm loud. So acceleration is down and 9.80 meters per second squared. What's our abbreviation for 9.80 meters per second squared? Little g. Little g. Right. Good. Excellent. On the way up, is the ball speeding up or slowing down on the way up? Slowing down. Slowing down on way up. And the reason I ask that is, what did it speed at the bottom? Was it speed higher or lower than the speed it had when it passed the window?
Higher.
It would have to be higher because it's slowing down all the way up, right? So when we do the calculation here, as they ask for what's the initial speed, if I don't get a number bigger than 16, I better double check what I did. All right? Just like, does it stop going up before it gets to the window or after it gets to the window? What do you think? Does it stop moving up before it gets to the window or after it gets to the window? After. Because at the window it's moving upwards at 16. How fast is it going to be moving up when it gets to the top? 0. So if I get an altitude for B less than 20 meters, I better check my math again. All right? And how long did it pass the window? After how many more seconds does it reach the street again? So these all have, so I think these are the main understandings to have here. Let's see. Here. Going down the way up, probably at the top, it stops. How long does it take to go up compared to how long it takes to come down? Same. Same time up and down. Alright. I think I need a little picture to remind myself things here. Let's see. We'll do this in a minute. So, ball starts here, goes up, turns around, comes back down to here. I've got this window here. In this case, it's moving up. Here, it's moving down. That's the ground. What position do you want to say the ground is at? 0 meters. Okay, good position. So that means that this window is at 20 meters, right? And I know that this whole time it's accelerating down at 9.80 meters per second squared. Which way do you guys want to call positive? Up, okay. Call up positive. And, oh, I know that right here, draw that up. That's lots of stuff. Right here, it's going at 16 meters per second upwards, right? Yeah. And up top here, I know it's not moving. V equals 0. Let's call right here, let's call that velocity at the start, V sub s. Yes? Is that okay? What should we call, we'll see if we need that. So the first part asked me about what was its initial speed. So I want to know what this Vs is. I know that in moving 20 meters while accelerating, it goes from that speed down to 16 meters per second. And so I look at my equation sheet and I say, do I have any equation that talks about I changed my speed because I accelerated and went a certain distance? Well, that's this one right here, right? I end up going this fast because I started going this fast and I accelerated as I moved through this displacement. So that's the one I grab. Yes, sir. In the problem? Well, it says after how many more seconds does it reach the street again? So I'm assuming it went up and came back down. Yeah, but you're right. Right now, we don't know that it did. We know that it reached the maximum altitude in B. So as we go down and they ask about stuff, I've kind of pieced together what happened. But you're right. At this point, we don't really know what happened beyond the window yet. So for part A here, part A, that we're saying that's the velocity it had at the start. That's for start. The V final, that's the final velocity of the part I'm looking at, and that's when it reaches the window. So that's 16 meters per second. That's squared. My V initial, that's my Vs, which I don't know, squared, plus 2. My acceleration's down, so that's negative 9.80 meters per second squared. Oh, the 16, I better make that positive, right? Because it's upwards. I gotta keep my signs in there. And then my delta D, it goes from 0 to 20, so that's positive 20 meters. Because we said up was positive, and since the acceleration's downwards, I gotta make it negative. Say it again, sorry. During the whole time, the acceleration is down. That's because it's in free fall. In free fall, the fact that it's locked in, that we know no matter what, is that our acceleration is downwards at 9.80 meters per second. Yeah. So now I just solved that, and I end up with 25.5 meters per second, the velocity it started with. Moving on to part B. In part B, I want to know how far it goes if it starts, how far it goes till it gets to 0 meters per second. Because remember, at the top it stops, right? That's our condition to turn around at the top. We got to go down to a velocity of 0. So I'm going to stick with the same equation. Would it make more sense for you guys to do it from 20 meters up or to do it from the ground up? Think about that over lunch. We'll come back to this. So in part B, they want to know what altitude does it reach. And we know that at the very top, it has to stop for that millimicrosecond before it comes back down. So at the very top, it's going to be going 0 meters per second. Okay? And it started at the bottom at 25.5 meters per second. Plus 2, it was still accelerating at negative 9.80 meters per second squared. And we don't know how far it went. Let's just call that h. So in a distance of h, you've got to go from 25.5 meters per second down to 0 meters per second. Oops, squared. And then we do our fun math. Come out to be h is 33.1 meters. We're close. Now, the next part that it wants, part C, is how long after it was thrown did it pass the window? Well, we know that when it went by the window, it was moving at 16 meters per second, and we know that it traveled 20 meters. We know now that it started moving at 25.5 meters per second. We know that during the whole time it's accelerating. And so if we look and say, okay, well, let's see. We know how it started. We know how it's going when it passes the window. We know how far it's traveled when it's past the window. We know how it's accelerating during this whole time. And we want to know how much time it took to get there. We really know so much that we could either use either equation, right, to figure out how long it took to get up to that window. I'm going to pick the second one. I'm going to pick this one just because it seems to, for T, be a little bit easier to solve for T. So, this is part C that we're doing right now. So I know that when it gets up to the window, it's going positive 16 meters per second. It started going positive 25.5 meters per second. It's accelerating at negative 9.80 meters per second squared for some amount of time t. Do the magic math, and I get t is 0.965 seconds. So it takes almost a whole second to get up there. Yes? No? Maybe? All right. Let's look at this last part. In the last part, I want to know, after how many more seconds does it reach the street again? So it's saying from here, how long does it take to go up and then come back down to here? What do I know about when it gets back to the street? What are a couple facts I know there? It's back at a position of 0. Good. What else? Which way is it moving? Downwards. How fast is it moving down compared to how fast it was moving when it started? Same speed because of that symmetry there. So it's going actually VS but downwards, right there. Yes? Yes? No? I'm going to use that fact to help me out down here. When I do D, I'm going to use my same equation again. When it gets down the bottom, it's moving at negative 25.5. It's a negative downwards, meters per second. It started at the window at positive 16 meters per second plus negative 9.80 meters per second squared and T. Solve for T, and I get 4.23 seconds. That's how much time it takes to go from 16 meters a second to our negative 25.5 meters per second. Very important that you get the signs right on that to make it work out correctly. All right, we're on to number 5. While riding a hot air balloon, which is steadily descending. Ooh, descending meaning going which way? Down. You actually drop your cell phone. After 3 seconds, what is the speed of the phone? How far is the cell phone below the balloon at this time? What are your answers in parts A and B if the balloon is rising steadily? So, 2 very important factors here that would need to be in your Y. The first one, hopefully by this point, is fairly obvious. The phone is in free fall, so A is down and 9.80 meters per second. All right, hopefully by this point, everyone's got that in every one of their Y's for this assignment. The other factor, though, that you may not at first realize is the fact that when it is released, when it is dropped, your cell phone is moving with the same speed, same velocity as the balloon. All right? So before, when we did a drop problem, we said the velocity when you dropped it was 0. Well, that's because the person who dropped it wasn't moving with respect to the Earth. They're just standing there. Here, if you're in the balloon and it's descending, and you drop something, its initial velocity is the same as the balloon, because it is 0 compared to the balloon, but not compared to the Earth. So the phone's starting velocity is the same as the balloon. Same as the balloon. So in the first case, it's downwards with the balloon. In the second case, it's going to be upwards with the balloon. All right? And if we were to draw those, you know, here's our happy little balloon, right? Let me draw that. Yeah, that's good. If the balloon is moving downwards, then dropping the cell phone is going to look like this. But in the second case, the balloon is moving upwards. What's the path of the cell phone going to look like if it's dropped from the upwards moving balloon? It's got to go up until it does what? Until it stops, and then it'll come down. So if the balloon is moving upwards and you drop your cell phone, it actually moves up and then comes back down. Where if you're moving downwards and you drop your cell phone, it just goes straight down. All right? But in the second case, it's got to go up until it stops, and then it comes down. because you're going up immediately faster than it is, it doesn't look to you in the balloon like it goes up at all. But if you watch it from the outside, you'll see the ball go up, the cell phone go up, and then come down in that second case. All right? So, in the first case, after 3 seconds, what is the speed of the cell phone? So they're asking me, how does the speed change because of it accelerating for a certain amount of time? And that's what this equation talks about, right? I end up at this speed, this velocity, because I was accelerating for a certain amount of time. So this is A. So I want to know how fast I end up going. I start, which way do you guys want to call positive, up or down? Up, okay. So I start at negative 2.16 meters per second. I'm accelerating at negative 9.80 meters per second, and I do that for 3 seconds. And am I speeding up during this time? Yep. So I end up at 31.6 meters per second. And they ask me, what is the speed? So should speed be positive or negative? Positive because it just scale. It's how fast you're going, not what direction. I need to keep my negatives in there, otherwise, if I have one negative and not the other one, it won't be a happy camper. But then moving on to part B, unless there are questions on part A. Nope. Yes? Moving on to part B, how far is the cell phone below the balloon at this time? So I want to know where it is, and I know a lot about the time and everything, so I'm going to grab this one. And extend my page again. So I want to know where it is. I'm going to call where it started at the balloon at 0 meters. Its initial velocity was downwards again at 2.16 meters per second. It moved for 3 seconds. Over. There we go. Plus 1/2 negative 9.80 meters per second squared, and 3 seconds squared. All that comes out to 44.1 meters. Below the balloon. The original position, either displacement original and it's the naught. It's be picky. But it's where it started. And we're calling where it started as the balloon. Yeah, and I called that 0 because I want to know how far below the balloon it is. So, all right. That was part B. Let's move on to part C. In part C, they say, what if the balloon is now rising steadily at 2.16? So part C, I'm going to use the same equation as I used for part B, but this time it's going to be going up. So if you remember for part A, that V final equals V initial plus AT. My V final is what I'm looking for again. My V initial this time is 2.16, that's positive 2.16 meters per second, plus negative 9.80 meters per second squared times 3 seconds. going to end up being going faster or slower than it did in part A? What do you think? This time, its velocity is up, but its acceleration is down. So what is it doing initially? Those are in opposite directions. Slowing down, speeding up, or staying at the same speed? Slowing down, because the velocity is up and the acceleration is down. So it's going to slow down and then speed up. So within that 3 seconds, it's either just slowed down the whole time, or it could have slowed down and stopped, or it could have slowed down, stopped, and then started speeding up again. So my guess is it's going to be a lower speed than part A, because in part A, all it had to do was speed up for those 3 seconds. Now it's got to slow down for all of it or part of it, and then speed up for whatever's left over. And we end up with a velocity of 27.2 meters per second. So it is less because it was slowing down and then speeding up. And we actually end up with, that would be a negative answer, but we're looking at speed again, and so we're just taking the positive. Because negative 9.8 times 3 is about negative 30, and you add that 2.16 to it, and you get negative 0.7. Yeah. In just reading what they said, what's the speed? Speed, I know, is the magnitude of the velocity. That's how big the velocity is. So I'm going to get negative. So when I did my math here, I actually got negative 27.2 meters per second. I knew that negative just meant direction. So the speed, the velocity is negative 27.2 meters per second. The speed is 27.2 meters per second. The negative just means it's going down. And with speed, it's like your speedometer. It never tells you what direction you're going in. It just tells you you're moving at this rate. If it said, what's the velocity? Or it said, what direction is it going in? By getting the negative, you know it's going down. And then up to D. In D, I'm using the exact same equation again. I'm looking for where it is. I'm going to call where it started 0 meters again. Its initial velocity is at positive 216 meters per second. Time is 3 seconds, plus the 1/2. Everything's the same except for that initial velocity. And 3 seconds squared. Do you think it's going to be further from it or closer to it? What do you think? Any opinions? No? Let's see. Oh, wait a minute. Is that going to tell us how far it is from it? Or how far it's fallen? Oh, we may have to rethink these then. Because does the balloon stay where it was? Or does the balloon keep moving? It keeps moving. So, like this, and that's where, that's why those numbers didn't seem to work out. So this, I'm going to erase here. This will tell us, part B here tells us where the cell phone will end up. But the balloon doesn't stay in the same place. It's not like the side of the cliff. All right? So the balloon is going to keep moving. So we need to do, so this is for the phone. This is for the phone. And so D, let's call that D sub P, D for the phone. We also need to do this for the balloon and figure out where the balloon is. So for the balloon, we're back on B. The balloon, was originally moving at negative 2.16 meters per second, and it moved for 3 seconds. What's the balloon's acceleration? Right, 0. So, we are back up on B. So let's get my up a little more here. So, where the phone is, the phone is at negative 21.18 meters. The balloon is at negative 6.48 meters. Sorry, just double check something. Oops. Sorry, not negative 21.8. I missed the sheet. At negative 50.58 meters. And so if it's at 50.58 meters and the balloon is at 6.48 meters, they are 44.1 meters apart. So if here's where the phone is, here's where the balloon is, that's how far they're apart. Moving on to part D, to redo D. This is where our balloon is. This is where our phone is. And then our balloon starts at the same point, 0 meters. It's moving at the 2.16 meters per second for 3 seconds. It's not accelerating, so that's all 0. So my balloon, let's see, 2.16 times 3 plus 0.5 times negative 9.8 times 9. I get my phone is at negative 81.22 meters. That's the position of my phone. My balloon is going to be at 6.48 meters. So the difference between those is 87.7 meters apart. Hold on. This is an 81, 82. That seems completely wrong to me. This is negative 37.62. And that is 44.1 meters apart again.